Hello IB students, today we'll be solving three questions from rigid body dynamics. Let's start with the first question. A solid disk of radius 5.5 centimeter is placed at the top of a 1.5 meter ramp. It rolls down without slipping and reaches the bottom in 0.96 seconds. The first question is write the relation between linear distance and angular displacement. So we have a disk whose radius is given. The disk rolls. It rolls down the slope and the length of the slope is given to us. It is 1.5 meter and we are given the time it takes to roll down. The first question is what's the relationship between L and the angular displacement? Angular displacement means the angle the disk has rotated. As the disk rolls and reaches the bottom, let's find the number of rotations. The number of rotations represented by letter N would be given as L divided by 2 pi r. Why is that? That's because 2 pi r means one rotation and L divided by 2 pi r is going to give us the number of rotations that it must take place in order to cover a distance of L. And what's the angle? Well, angle would be the number of rotations times 2 pi because one rotation is an angle of 2 pi. So I'll substitute this value of L over 2 pi r in place of N. If I do that, I get L over 2 pi r times 2 pi. 2 pi goes away and we have our expression. The angular displacement is related with the linear displacement L given by this equation theta equals L over r. So that's the first part of the problem. The second part of the question is calculate the angular acceleration of the disk. We know the angular displacement. We also know the time. So why not use one of the angular Suvat equations? That is theta equals omega naught t plus half alpha t square. All right, we want to find alpha. T is given, theta is given. And what's omega naught? Omega naught is the initial rotational velocity. Since the object was released at rest, omega naught is 0. So this entire term goes away and I have theta equals half alpha t square. I can rearrange this for alpha. I get alpha equals 2 theta over t square and I can get theta from this equation. So upon doing that, I have 2 L over R t square. Now all we have to do is plug in the values. Plug in the value of L, R, and T. And both of them, all of them are given R, L, and T. Let's plug in the values. We have 2 times 1.5 divided by 0.05 times 0.96 square. Time to use our calculator, which gives us a value of about 65.1 radians per second square. So that's all the second part. Let's move on to the third part of the problem. A solid wheel and a thin ring, both with the same mass and radius, are placed at the top of the same inclined ramp. They are released simultaneously from rest and roll down without slipping. Without doing any numerical calculations, explain which object will reach the bottom first. We know that the ring, all of its mass is distributed away from its rotational axis. So if we take a ring, and this is the rotational axis, all of its mass is distributed away from the axis. And what does that mean? That means the moment of inertia is going to be large. In fact, the moment of inertia of a ring is mr square. On the other hand, if we look at a disk, some of the mass is very close to the rotational axis. That means its moment of inertia should be lesser than that of a ring. In fact, the moment of inertia of a disk is half mr square. All right, so this is moment of inertia of a disk. This is moment of inertia of a ring. This means that it's easier for a disk to rotate, to roll, rather than for a ring. Ring has larger moment of inertia. It's very resistant to rolling. So the disc is going to reach the ground first. Okay, so that completes the first question. Let's move on to the second one. A uniform horizontal rod of length 6 meters and weight 40 newtons rests on a frictionless pivot located at its left end. A vertical support placed at 4.50 meters from the pivot keeps the rod balanced horizontally. Calculate the magnitude of the vertical upward force provided by the support. So the situation looks like this. We have a rod, it's pivoted on the left end, and we have another support over here. All right. We are interested in finding the magnitude of vertical force by the support over here. Okay, let's try and do that. We know that the rod has a weight of 40 newtons. So we can assume it to act at the center of the rod. The rod has a length of 6 meters. So its center is somewhere here, 3 meters. And that's where the weight can be assumed to act. We are given that the weight is 40 newtons. This distance is 3 meters. All right. So we can find the torque about the support, about the hinge. The torque due to the weight, it's going to be distance times the force. That's 120 Newton meter. And this torque is trying to rotate the object clockwise. So this is a clockwise torque. This support is going to push upwards on the rod. So let's write that as Fs. Fs stands for force of the support. And what would be the torque of the support? It would be its force times the distance, which is 4.5. And this torque is counterclockwise. So CCK. Okay, all right, that's a shorthand for counterclockwise. Since the rod is balanced, the clockwise torque must be equal to the counterclockwise torque. So these two have to be equal. Let's equate them. We have Fs times 4.5 equals 120. Now we can solve for Fs. It's going to be 120 divided by 4.5. And how much is that? It's about 26.7 newtons. So that gives us the force of the support, 26.7 newtons. All right, let's move on to the next part of the problem. Suddenly the support is removed and the rod begins rotating clockwise about the pivot. The rod has a moment of inertia 30.6 about the pivot. Calculate the rod's initial angular acceleration. Since this support has been removed, there is no upward force on the rod. We just have the force of gravity, which is 40 newtons. That's acting 3 meters away. So the only torque acting on the rod is 120 Newton meter due to gravity. We also know torque equals moment of inertia I times alpha. All right, so I can substitute it here and I get 120 equals moment of inertia times alpha. That means alpha is 120 divided by moment of inertia. That's 120 divided by 30.6. If you plug it into a calculator, we're going to get alpha as 3.9 radians per second square. So that's our value of alpha. Explain clearly why the equation theta equals half alpha t square cannot be used to determine the time taken for the rod to rotate from horizontal to vertical position. So the rod, when the support is removed, is going to fall. The question is, why can't we use this equation? All right. The answer to that problem is that the torque is not constant. The torque due to gravity is not constant. When the rod is over here and gravity acts down, so you can easily calculate torque by multiplying force and this distance. Now, when the rod rotates, let's say it reaches this end, the force is vertical and the distance is pointing along the same direction. This means that the torque is zero. This means that the torque is not constant. If torque is not constant, alpha is not constant. So if alpha is not constant, we cannot use these Suat equations. Suat equations are only applicable when alpha is constant, right? Let's move on to the next part of the problem. At the moment the rod becomes vertical, show that the angular speed is 2.80 and calculate the angular momentum of the rod. All right. So how do we solve this problem? We can use energy conservation. So when the rod swings down and reaches its vertical position, what happens to its center? The center is over here and the center is over here. So what's the distance the center has fallen? The distance the center falls is half the length of the rod, that's 3 meters. Now that's the decrease in potential energy, mgh, where h is 3 meters. That must have been converted to kinetic energy of the rod. Kinetic energy of the rod is half I omega square. That's the kinetic energy of a rotating object. Now we can solve for omega and we have 2 mgh divided by I under a square root. We know all the variables. We know m, we know g, we know h, we know I. So if you plug those values, you get a value of about 2.80 radians per second square. And finally, we are supposed to find the angular momentum of the rod. The angular momentum equation is L equals I omega. I is given to us. We can use the value here, 30.6. That's the value of I. And omega we just found is 2.8. This gives us a value of 85.7. So that's the value of L. Let's move on to the third question. A constant torque is applied to a horizontal disc of mass 0.25 kilograms and radius 0.30 meters. Initially at rest, the disc begins to rotate. The graph shows the variation with time of the angular speed omega of the disc. The moment of inertia I of a disc about a vertical axis rotating through its center is given as half mr square. The question should have said that, but that's a typo. So it's given to us that the moment of inertia is half mr square when a disc rotates about its center. All right. The first question is, show that the angular acceleration of the disc is about 5 radians per second square. We know alpha is given as the rate of change of omega. This rate of change of omega is simply the slope of this line. So how much is this? Rise over run. The rise is 10 and the run is 2. So 10 over 2 gives us 5 radians per second square. That solves the first part. Calculate the torque acting on the disc while it accelerates. We know that the torque applied on an object equals I alpha. I is given as half mr square and alpha times alpha. So we can use half, mass is given to us 0.25, radius is 0.30 square times alpha. So we need to plug this into our calculator and we get a value of about 0.056. So that's the torque acting on the disc. While the disc rotates at its initial constant angular speed, a 0.10 kilogram object is dropped vertically onto the edge. The object sticks to the disc and moves with it. So the disc is spinning and we drop an object onto its edge. We have to figure out the new angular speed of the system. So these types of problems are very common in your final exams. So if you take the disk and the mass as a system, there is no external torque that's trying to spin it faster or slow it down. If that's the case, the angular momentum has to stay constant. Initial angular momentum of the system before the object falls onto the disk must be equal to the final angular momentum. What's the initial angular momentum? Initially, the disk is rotating and its angular momentum will be given as moment of inertia of the disk times omega. What's the final angular momentum? The disk still is rotating but with another omega. So it would be I disk times omega final plus. Now since the mass is also rotating in a circle, it's also going to contribute to the momentum. So what's the contribution due to the mass? It will be the moment of inertia of the mass times, and it's rotating with the same omega. Alright, so simplifying this would give us moment of inertia of the disk, omega final, plus moment of inertia of the mass. It would be m r square. M is the mass of the object, r is its distance, times omega final. Let's solve for omega final. We get id omega divided by id plus mr square, right? We know the moment of inertia of the disk. It's half capital M stands for mass of the disk, r square omega divided by half mr square plus small m r square. R square cancels throughout, and we can rearrange this equation and get m omega divided by m plus 2m. Alright, we know the mass of the disk, we know the mass of the object that fell onto the disk, we also know the initial angular momentum. So let's plug in all those values. Mass of the disk is 0.25, its radius is 0.30. So mass of the disk is 0.25 divided by 0.25 plus 2 times mass of the object that falls on the disk, which is 0.10. So that would be 2 times 0.10 times omega, the initial rotational speed. Initial rotational speed is 10 radians per second. So we'll write that. So putting this into our calculator, we get a value of about 5.5 radians per second. Final part of the problem, determine the fraction of the total energy of the disk that was lost. So if we compare the final rotational speed with the initially it was rotating with 10 radians per second, and now it's rotating with 5.5 radians per second. That means the disk is moving slowly. This therefore means that the energy has been lost, and we are supposed to find that. So you can take this part as a homework. Drop your answers in the comments below and I'll get back to you. I'll see you in the next video. Happy learning.